Hey everyone! So in class today, we spent a lot of time looking at the translational motion of single points on a rotating object. So we were looking at maybe this wheel here that is spinning, and even though the entire wheel or disk itself is not actually translating in space, we saw that individual points are. Individual points on this rotating circle are in fact moving and have linear velocity, linear displacement, all these linear or translational quantities. What we're going to be looking at in this video is also a connection between translational and rotational motion. But instead of looking at this motion of these individual dots on the object, we are going to actually be looking at a situation where the entire object is not only rotating, but the entire object is also translating. So notice each individual point is both rotating and translating, but notice the center of mass of this entire wheel is also moving in space. So that's what we're going to be looking at today, describing the relationship between this rotation and this translation. Now, in general, rotational motion, the speed at which something is spinning, and translational motion, the speed and rate at which it's moving through space, are completely independent of each other. One motion, the translational, does not necessarily affect or be related to the rotational motion. So, just as an example, if I have this wheel here, it can obviously rotate. Not sure how well that's coming through the camera, but hopefully you can see that this is rotating, rotational motion. But a wheel can also undergo translational motion, so changing its physical location in space, moving linearly, and it can also do both at once. Now, when I say these two motions are independent of each other, that means that I can have this thing spinning slowly and translating slowly. Notice slow rotation, slow translation. I can also, however, have this thing rotate quickly, but still translate pretty slowly. Notice, even though the rate of rotation increased, my translation did not. These are independent of each other. And again, I can have this rotate fast and zoom, translate really fast. Again, those two things are independent. I can also have this rotate, slowly, but translate quickly. Notice the speed at which this thing is rotating really has nothing to do with the speed at which it is translating. These are controlled by two very different things. The speed at which it's rotating depended on, well, how quickly my hand rotated it up here at the rim. But the translation is, well, me holding it here at the point axis, whatever this is. Notice these two things are independent of each other. The speed that it is spinning is not at all connected to the speed at which I am translating it at. Now, this idea really is the case for a lot of spinning objects that are also maybe flying through the air. For example, a frisbee. You can rotate a frisbee really fast, have a lot of spin to it, but have it barely moving across the field. Same thing, you can throw a frisbee across a field, but not have it spinning really quickly. Those are two independent things. And the big idea, let's say I tell you that this frisbee is flying through the air at 3 meters per second. This is going to be a translational velocity. This is not enough information for us to figure out how fast it is rotating. It could have any angular velocity and still be flying through the air at 3 meters per second. Again, in general, there is no connection between the rate at which this thing spins and the rate at which it translates. There is one situation, though, where these two motions, rotational and translational, are completely locked into each other. There is one situation where these two motions are going to be connected, and we can use one to predict the other. So there is one situation where this wheel, if I cause it to rotate faster, spinning, it is automatically going to translate faster, move horizontally. And the only subtle change that I have to make to this wheel is put it on a surface. Instead of having it just spinning in the air, I need this object to roll, to have a rolling motion. So let's look what happens when I begin to translate slowly across the room. I'm going to move at a pretty slow speed. Watch the wheel and watch the rate at which it rotates as I translate slowly. Maybe just watch this point here. So again, pretty slow translation. Notice fairly slow rotation. Nice steady rate. Now on the way back, I am going to translate faster. I'm going to change my location in space from one side of the room to the other. I'm going to do it, I'm going to try to do it like 3 or 4 times as fast. I'm just going to sprint to the other side of the room while this wheel is on the surface. And again, I want you to watch now the rate of rotation. As I translate faster, with this wheel now touching the surface, what happens to that rotation? Very obvious, as I translated quickly, this wheel rotated very quickly. There is no way that I can translate quickly, but have this rotate slowly. As I speed up, notice the wheel speeds up with me. The faster this rotates, the faster the translation of the wheel also matches. Slow translation, slow rotation. Hopefully you can see this little marker on the side. Fast translation, fast rotation. These two motions are locked into each other. And this is the essence of how cars and bicycles work. Your engine is not actually speeding up the car itself. It is increasing the rotation of the wheels. As you are pedaling a bicycle, you are causing these wheels to spin at a faster rate. And as the wheels spin faster, the wheels begin to translate faster. Those two motions are connected. And of course, the bike or the car is then connected to the wheel, kind of like I was, and the car ends up translating faster as well. This type of motion, where the rotation and the translation are locked into each other, this is called the rolling motion. With this rolling motion, this is not true for all rotating and translating objects. This is only specifically for objects that are rolling along a surface. And in this situation, as we saw, there is that relationship between the angular velocity, omega, and the translational velocity, the typical one that we are working with. If we increase or decrease the rotational velocity, we will see the translational velocity follow. And by definition, the way you will know that we are looking at this situation, you will see in problems, in statements, that a rolling object is moving across a surface specifically without slipping. And this is really talking about our condition for static friction that we talked about with wheels. When wheels are rolling along a surface, they are not sliding against the surface. They're basically gripping on to a single point on the surface, and the wheel is rotating above it, kind of like a cartwheel. That was always the metaphor I use for tires that are spinning. We do have to see rolling without slipping. That means each point of contact on the tire is only making one point of contact with the surface and vice versa. So once we know that there is truly, in fact, a rolling motion, we are rolling without slipping, can we use the rate of rotation to predict translation, or can we use translation to predict rotation? Can we use one motion to predict the other motion? And the answer is definitely yes. There is a nice connection between how fast the wheel is spinning and how fast it is translating. So let's look at this for a moment. So let's look at the connection between how far this rotates and how far it actually moves. So what I'm going to have this wheel do is I'm going to have it rotate through exactly 1 revolution, or 2 pi radians of angular displacement. Basically, this wheel is going to spin exactly around once, but we are going to do it with the rolling motion here on the surface. And I want us to pay attention to how far this wheel translates through space. So I'm going to use this nice green thing kind of as a marker to signify where we started. That will allow us to make sure we have stopped the wheel after exactly 1 revolution. And I know our classroom camera, the angle is a little bit off just because it's a very wide lens, but I'm currently starting the center of this wheel right above the start of this purple mark. So the center of the wheel starts right here. So I'm basically tracking both how far I move in purple, but also how far I rotate. So I'm going to go through 1 full revolution, 2 pi radians, rolling without slipping. Stop it right here. Now, notice I've pre-planned this purple. Again, we are now on the weird side of the classroom camera, but if we follow this straight down, this wheel has now translated this purple length of tape as it rotated through 1 revolution, or 2 pi radians. This purple is the translational distance that corresponds to exactly 1 revolution, 1 full rotation of this wheel. So before we actually measure how far this wheel moved, looking at this purple piece of tape I have out, let's just try to think about and predict how far it actually would have moved. So we have made one full revolution around this circle. And like we talked about, rolling without slipping, that means every single point on this wheel came into contact with exactly one point of contact here on this surface. So as this wheel was rolling out, every single part of this outer edge of this wheel of maybe radius r came into contact with exactly one point of this flat surface. As we go all the way around, by the end, we will get back to the beginning. So if this is location A on the wheel, maybe here is B, it'll roll down, put down B, keep rolling, 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 maybe to the top, to the end, then eventually the wheel ends up right in its initial position. And just to kind of show this visual one more time, what I tried to show on this board, as this wheel is rotating, A starts here, then as it spins, B gets laid down, this translational displacement, C, D, all the way back to A. So how can we predict this translational displacement? Well, one thing you might have noticed is if it is this outer edge of the wheel that's basically laying down its length onto the track, it would make sense that this length on the track is the length around this circle, which we know as the circumference of the circle, or 2 pi times the radius of that circle. If we have gone once around this circle, we have gone a circumference of 2 pi r, the circumference of a circle. Now this is really interesting because we know our theta, our angular displacement for this situation, was already 2 pi. So we can actually make a translation. Our circumference is our distance traveled, linear distance of this object, is going to be our angular displacement theta, 2 pi, times the outer radius of the circle. This equation here, distance equals angular displacement times the radius, should look familiar because this is our angular translational translation from angular to translational or linear motion. The distance that this outer edge moves around the edge of the circle is actually going to be the same as the entire tire translates, as long as the radius that we use is again the radius of the edge that is in contact with the surface. We don't want to use any of these points inside of the circle. That won't work. That's not going to be the right radius. As long as we use the outer radius of that rolling object, then we can say that the distance this object is going to move is equal to the distance it rotates, that angular displacement, times that outer radius. Now, just to quickly prove that this in fact is the circumference, I'm going to pick this piece of purple tape up. And I'm just going to wrap it around my tire, just to show that this distance that this object in fact spun is the same as the circumference, 2 pi r, of the outer edge of the circle. So I'm just going to quickly keep that there, wrap it around, and you can see it looks pretty big, but when I get back to the beginning, I'll try to zoom in, but this perfectly locks once around this circle. That translational displacement from left to right was exactly the radius, nope, not the radius, the circumference of this tire. There was this really nice relationship between the distance and the circumference. And that allows us to use our equations relating distance and angular quantities to each other. So the big question is, well, what does this help us determine? Well, this tells us that if we know an object, so a wheel, a can, a disc, anything is rolling without slipping, so is actually going through a true rolling motion on a surface. So again, it's not spinning in the air, it's not flat, it is rolling on a surface, and let's pretend that this is a perfect circle. The If this is rotating, so it has maybe some angular velocity, it is going to go through an angular displacement theta. As it is rolling, it is also going to translate a corresponding displacement and have a corresponding linear velocity. Distance velocity will correspond to the angular velocity and the displacement. And same thing with the acceleration. But this entire object, so this entire wheel, if we wanted to predict, again, its displacement over here and the time, speed, all of it to get there, we can use the radius for the edge of this rolling object, because again, it is this point right here, right on the surface that is actually in contact with the surface, to make these translations. So if the entire wheel goes through a rotation theta, we can predict the displacement of the entire wheel. How far does it actually move from left to right, up or down, whatever direction it is rolling? As long as we use the radius to the edge of the wheel. That's the big key thing. This always has to be to the very edge of the wheel, not any of the points on the inside. This also works for velocity. If we know omega, the angular velocity, we can make a conversion to how fast the wheel is actually translating the linear velocity. And of course, if this wheel is speeding up, if it is moving faster and faster, this wheel will also accelerate. In terms of translation, it's going to speed up, kind of like a car. If your car is accelerating meters per second squared, the wheel is also accelerating angularly. So in the guided notes, there are a couple of examples for you to work with using these equations for, again, the outer edge of the radius of the thing that is rolling without slipping. These are in your guided notes, but I will also put them in this Google Classroom assignment. Give these 3 a shot, and then I will post a second solution video just so you can see if your answers are correct.